My name is Dan O'Gara. I'm a retired engineer from the University of Hawaii Institute for Astronomy. I worked here for 37 years. Initially hired in 1984 to work on the lunar ranging experiment, which was actually started up on the summit here of Haleakala in 1972 to support the Apollo program. At the time, they only had two sites. They had three sites. There was a place in southern France, in Grasse, outside Grasse, and there was the McDonald's Observatory in Texas, and they wanted another high altitude site here at Haleakala. So when I got here in 1984, they still had not been very successful in getting data back from the moon. And I guess we should go into a little what that is. The lunar ranging uses a pulsed laser to fire pulses at the moon, and they time the pulse, time of flight. And with that information, you can get distances. And with those distances, you can create orbits of the moon, very, very accurate orbits. And there was several sites on the moon that were set up with reflectors by Apollo 11, 15, 14, and there was 3 Lunokhod Russian reflectors up there, and different spots on the face of the moon there that we see. And with the range information to all those different sites, you can find out how the moon is wobbling and how it's moving very accurately. So we don't do that here anymore, though. We did that from '84 when we first started getting data, and by 1990, NASA cut funding for lunar ranging. It's still being done around the world, and the accuracy of the orbit is in the order of a few centimeters probably now. It's very accurate. After they shut down, while we were doing lunar ranging, we were also starting to track satellites. It was in the mid-'70s when NASA and France put up geodetic satellites, just big lumps of very massive material that they were using for, at the time, they were using it for positional studies. If you have multiple sites around the world that were tracking these satellites, you get basically a reference point in the sky, and you can get the distances between these points. I think that was really the first time that scientists were able to measure continental drift almost in real time. They also were able to measure the gravity field very accurately, because these positions, the satellites are accurate to within down to a few millimeters. So they can actually see changes in the orbit that are caused by gravity, both the static and dynamic gravity field. And the third thing we do besides the geodetic studies are supporting the Earth sensing satellites. That's taken over quite a bit of the work lately, because in order for these satellites to measure the sea height and the ice pack, and they need to know where they are very accurately. And so the information they get from our data, the orbit data, they were able to calibrate their instruments very accurately. And I guess one more thing I forgot about is we also support the GPS, the global navigation systems, for the same reason. They need to correlate their data. Actually, what they use, I think, most frequently is the Earth center. The laser data that we get, the range data, from that data you can calculate the center of the Earth very accurately, and that gives them a reference point to their orbits. So it increases the accuracy of the global navigation systems. Right now there are probably, the global navigation system satellites have almost taken over the sky. There's probably, the ones that NASA supports, there's probably 15 or 20 of them or more, and they rotate in and out as they go out. I could show you the International Laser Ranging Service is the international service that supports laser ranging around the world. They correlate the data, and they data accuracy and standards for observatories. And so through that organization, NASA, European Space Agency, all the space agencies go through that system in order to disperse the data to scientists. So this basically all we've done is just use a laser to accurately locate satellites. That's fundamentally what it is. But it does, I mean, it actually supports all of those different disciplines. You know, like everybody uses GPS now, you know. And the reason they're able to claim that the sea level is rising by the amount it is because the data that they're getting is so accurate. It could be that accurate. I think I mentioned that the geodetic satellites, which are just big balls in space, are accurate to almost a millimeter, their orbits. The other satellites that have things protruding off of them aren't quite as accurate, but still within the centimeter ranges. So these satellites orbit the planet 24 hours a day, collecting data 24 hours a day. I think that's pretty much the synopsis of what we do. They've been sort of stuck for years, and we drove it down. I can show you plots of how quickly they drove the accuracy from meters, you know, to centimeters to millimeters. But it's been stuck at the millimeter level for a while. We're reaching the limits of the ability of our technology, I guess. But they're still trying, not going to give up. So, and also, I guess I did hear that they're going to put new reflectors on the moon for new science, lunar science, which, like I said, I just not involved in it, but I did hear at one of the meetings, one of the last meetings I went to before I retired, was that they were going to put these newly designed reflectors up on the moon and get back to doing more lunar ranging. Well, GWST, I was never involved in that. Of course, I pay attention to it. It's a fantastic instrument. That first deep field they showed, the fact that they got it in a few hours, I think it was 10 hours or something like that, compared to how many days it took Hubble to get something similar, and plus the depth of the field, it's just mind-blowing when you think about it. It's going back to within 300 million years of the beginning of the universe. I forget exactly what the time is, but it's much further back in time. And there's just, every time you look at those, you just think, you know, all those little dots out there are galaxies, and galaxies have billions of stars, and there's probably billions of planets. So yeah, it is sort of mind-blowing when you look at that. And I did actually see it. I was at a NASA meeting about 6-8 years ago, and I saw the JWST in their clean room. They had a clean room with a viewing port for people, and they were just, at that time, I think the mirror was partially installed, or it was folded over. I didn't see the whole thing opened up, but I did get a chance to see it. It's much larger than I thought. That is one thing I can tell you. When they launched that thing, I held my breath for days until they actually got it in orbit at that Lagrange point where they have it finally, because it's a hugely complicated machine. And as they've mentioned many times, if something breaks, they can't fix it. So it's a scientific and an engineering feat that's really mind-blowing. So I am interested in that. I am interested in the technology they use, and if you think about all the software they write for it too. How many lines of code, make sure, if you make a mistake, you can't fix it. So it was a wonderful success. It's generating some fantastic data. Well, the future of the laser ranging jobs, yeah. The one thing that's changed over the years is laser ranging, because of the increase in technology, has become more and more robotic. And the stuff I was doing, and they're doing right now, is actually putting all the observers out of a job, because when I first got here, we did lunar ranging. We tracked the moon and 2 satellites, Legios and Stella, I think, that was a French satellite. And we had 13 people on staff. So today we have a smaller site up top. I'm not sure if you went up top and you saw the laser site. It's just a transportable box. We have 2 people that run it, and they track something like 30-some targets now. The automation and the technology and the software, everything got so much better that you don't need 13 people to support it. And the goal is for NASA is trying to build these robotic systems. So this one up here, the laser station we have up here right now, is planned to be replaced by a fully robotic, remotely operated system. So at that point, there will be just one person, part-time person here on the island to do hardware maintenance. But they plan to have a central command center somewhere that will be working all the ones they have around the world. NASA has, I believe, 6 or 8 laser stations themselves. And there's a total of like 40, but by over 20 different nations that run them. But the NASA stations themselves, they'll probably end up having about, well, maybe 5 or 6 of them, and they plan to have them all completely robotic. So, I mean, I knew this was going to happen, and it was coinciding with my retirement pretty closely. So, the site up here is planned to be replaced within the next 5 years, from what I can tell. So, and actually the gentleman that's running the station now, he said that's going to work out fine for him because he'll be retiring in about 5 years too. So, but the actual collecting of this kind of data, I don't see it going away completely. You know, it'll become less labor intensive, less costly, and so they'll just keep collecting the data. You know. When I give presentations, I don't have it on the wall anymore. I used to have some posters on the wall. Basically, all we do is measure the distance from here to a satellite. That's really all we do. And that was my part of it. And of course, the scientists take that data and use it for whatever means. But the concept actually is this. It's very simple. You just want to measure distances between here and there. You know. And so it turns out to be a little more complicated than that when you get into the details, but that's really all it is. Yeah.